Galaxies are moving toward a secret we cannot see. This mysterious motion is called dark flow, and it defies the foundational rules of our universe. By the end of this journey, you will understand how a single cosmic anomaly could force us to redraw the entire map of reality. What invisible force is pulling thousands of galaxy clusters in one direction? Could this be a glimpse of something existing beyond the edges of our observable cosmos? How does it feel to stand at the edge of a discovery that questions everything? Our understanding of the cosmos rests on a powerful and elegant framework. It is often called the standard model of cosmology, a grand blueprint for how everything from the first spark of the Big Bang to the vast web of galaxies we see today came to be. At its heart is a simple yet profound idea. The universe began from a single, incredibly hot and dense point, and has been expanding and cooling ever since. Its large-scale structure shaped entirely by the forces of gravity and a mysterious form of energy we call dark energy. This model is like a master clockmaker's finest creation, a cosmic clockwork where every tick and tock, every galaxy's motion, can be explained by the interplay of these fundamental ingredients. And for decades, this clockwork has kept impeccable time. It predicted the faint afterglow of the Big Bang, the cosmic microwave background, with stunning accuracy. It explained how clusters of galaxies formed into the immense filaments and walls we observe. It became the bedrock of modern cosmology, a story we thought we understood. But what happens when the clock, for all its precision, begins to show a consistent, unexplained drift? That is the quiet, unsettling tremor introduced by dark flow. This is not a violent shattering of the model, but something more subtle and perhaps more profound. It is a directional whisper in the data, a suggestion that thousands of massive galaxy clusters are being gently tugged, not by anything within our observable universe, but by something beyond its very edge. Imagine our cosmic clockwork sitting on a table. According to all our rules, nothing outside the clock should affect its gears. Yet we detect a slight, persistent tilt, a lean in one specific direction, as if the table itself is on a gentle slope we cannot see. This anomaly does not mean the clock is broken. It means our understanding of the table, of the very stage upon which the universe unfolds, may be incomplete. Dark flow hints that our magnificent and self-contained model might be just one room in a far grander and currently invisible mansion. The cosmic clockwork seemed flawless until a satellite listening to the universe's oldest song heard a discordant note. For years, the Wilkinson Microwave Anisotropy Probe had been mapping the faint, cold light that fills all of space, the cosmic microwave background. This is the relic radiation from the Big Bang, a snapshot of the infant universe when it was just 380,000 years old. Scientists expected this ancient light to be almost perfectly uniform, a canvas of tiny temperature variations that told the story of how matter first began to clump together. A team led by researcher Alexander Kashlinsky was using this data in a clever way, not just to look at the light itself, but to see how it was being slightly distorted by the motion of huge clusters of galaxies moving through space. The technique is akin to listening to a train's horn. If the train is moving toward you, the sound's pitch shifts higher. If it moves away, the pitch drops. They were looking for a similar shift, known as the kinematic Sunyaev-Zel'dovich effect, in the microwave background light as it passed through these massive galaxy clusters. What they found was not the random, chaotic motion predicted by our models of cosmic expansion. Instead, they detected a startling signal. Hundreds of galaxy clusters, each containing the mass of thousands of Milky Ways, were all streaming in the same direction at incredible speeds, over 2 million miles per hour. This was not a local drift. The signal persisted out to distances of over 3 billion light-years. It was as if someone had drawn an invisible arrow across the cosmos, and everything on a colossal scale was pointing toward it. The scientific community was met with a profound mix of skepticism and awe. This coherent flow, this dark flow, suggested the gravitational pull of something unimaginably vast lying far beyond the edge of everything we can see. The quiet hum of the cosmic microwave background, the oldest story we know, was carrying a whisper from a place we did not know existed. This discovery presents a cosmic puzzle of the highest order. To understand why dark flow is so deeply unsettling, we must first define it with absolute clarity. Dark flow is not the grand, uniform expansion of the universe, the one that carries all galaxies away from each other like dots on an inflating balloon. It is also not the local, swirling dance of galaxies within our own galactic supercluster, pulled by the familiar gravity of our neighbors. No, this is something entirely different. Dark flow is a bulk flow, a coordinated collective movement of entire galaxy clusters, each one a metropolis of thousands of galaxies, all moving together across distances of billions of light-years. They are not simply drifting apart with the expansion. They are streaming as a single, immense river of matter in one specific direction. A helpful analogy is to picture countless leaves floating on the surface of a vast, calm pond. The gentle breeze and natural currents might push them in various, random directions, but if you were to observe every single leaf from one shore to the other, all slowly but consistently drifting toward a single, distant point, you would know something profound was happening. An unseen drain, perhaps, lies far beyond the horizon of the pond, exerting a pull that overrides all other local motions. That is the essence of dark flow. It is termed dark for the same reason we have dark matter and dark energy, because its source is completely unknown and invisible to our telescopes. It adds a third profound mystery to the cosmic ledger, a mysterious directional pull alongside the invisible cosmic scaffolding of dark matter and the repulsive force of dark energy. This is not a small eddy in the cosmic river. It is the river itself changing course, hinting that the landscape beyond our sight is not empty, but filled with structures of unimaginable gravity. The distances involved are almost impossible to truly comprehend. We are talking about galaxy clusters whose light has been traveling toward us for more than 3.5 billion years. When you look at the data revealing this dark flow, you are not seeing a local weather pattern in our cosmic neighborhood. You are witnessing a continent-scale current moving across an ocean that spans nearly half of the observable universe. The sheer scale of this coordinated motion is what makes it so revolutionary and so deeply challenging to our core beliefs. For over a century, cosmology has operated under a guiding rule known as the cosmological principle. It is a simple, elegant idea that the universe, when viewed on a sufficiently large scale, looks the same in every direction and from every location. It is homogeneous and isotropic, no special place, no preferred direction. This principle is the foundation upon which we built our entire understanding of cosmic evolution, from the equations of Einstein to our maps of the cosmic microwave background. It allows us to assume that what we see from our tiny vantage point is representative of the whole. Dark flow throws a wrench directly into this elegant machinery. A coherent stream of matter moving across billions of light-years is the very definition of a preferred direction. It suggests that on the largest scales we can possibly measure, the universe is not isotropic. There is a this way etched into the fabric of reality itself. This is not merely discovering a new galaxy or a strange quasar. This is finding a crack in the foundational assumptions of our science. It implies that our entire observable universe, all 93 billion light-years of it that we can possibly see, might not be the entire story. It might be tilting ever so slightly, under the gravitational influence of something lying far beyond our cosmic horizon. Imagine standing in a vast, seemingly endless plain. As far as your eye can see, the land appears flat and uniform in every direction, confirming your belief that you are in the center of a featureless expanse. But then you notice something subtle. Every single stream, every trickle of water is flowing not randomly, but consistently toward one specific point on the horizon. That single observation would shatter your understanding of the plane. You would instantly know that your field of view is not everything. There is a slope, a basin, a mountain range, something massive and unseen that dictates the flow of the entire landscape. Dark flow is that trickle of water on a universal scale, and it is pointing toward a mystery that lies over the edge of our map. Such a radical claim could not stand on a single data set. The scientific method demands verification, and the initial findings from the Wilkinson Microwave Anisotropy Probe ignited a firestorm of scrutiny. Other teams rushed to analyze the same data, searching for any possible error, any overlooked source of noise that could mimic such a profound signal. Could it be an artifact of the satellite's instruments, or a misinterpretation of the complex physics within the galaxy clusters themselves? The debate was intense, as it should be, for the stakes were nothing less than our fundamental view of the cosmos. This period of controversy was not a weakness of science, but its greatest strength, a rigorous gauntlet every groundbreaking idea must run. The tension would only grow with the arrival of a new, more powerful observer. Launched in 2009, the European Space Agency's Planck satellite was a technological marvel, designed to map the cosmic microwave background with unprecedented sensitivity and resolution. It was like switching from a standard telescope to one with a vastly sharper lens, capable of seeing finer details and filtering out more of the local cosmic static. The cosmology community waited with bated breath. Would Planck's pristine data confirm the dark flow, or would it reveal it as a tantalizing but ultimately false whisper? The answer, as is often the case at the frontier of knowledge, was profoundly ambiguous. Some independent analyzers of the Planck data did indeed find evidence of a large-scale bulk flow, a coherent motion that extended across staggering distances. It was not an exact replication of the earlier signal, but it pointed in a similar, unsettling direction. Other analyzers, however, reached a different conclusion. They suggested the apparent flow could be explained by more subtle, local effects, like the gravitational pull of known but undercounted superclusters of galaxies within our observable universe, or by complex interactions in the hot gas within the clusters that the satellites were measuring. The controversy was not resolved, it was deepened. Planck had provided more data, not less mystery. This ongoing debate sits on the razor's edge of modern cosmology. It is a testament to how difficult it is to measure something so subtle against the immense, roaring background of the universe. Every signal is fought over, every potential source of error examined under a microscope. The principle is sacred. Extraordinary claims require extraordinary evidence, and the evidence for dark flow, while compelling to some, remains locked in a battle of interpretation. This is not a failure, but the very process of discovery unfolding in real time. It means we are probing the absolute limits of our instruments and our theories, staring into a statistical haze where the next great truth of the universe might be hiding. The conversation continues, a quiet, persistent hum of inquiry that reminds us our maps are still being drawn. The controversy hinges on an almost impossibly delicate measurement. To detect the ghostly tug of dark flow, scientists needed a tool of extraordinary precision, a way to measure the velocity of objects so distant their light is a fossil. That tool is known as the kinematic Sunyaev-Zel'dovich effect, and it transforms the oldest light in the universe into a cosmic speedometer. Here is how it works. The space between galaxies in a massive cluster is not empty. It is filled with a superheated plasma, a thin but incredibly hot gas. When the ancient photons of the cosmic microwave background, that afterglow of the Big Bang, travel across the cosmos and pass directly through one of these clusters, they interact with the fast-moving electrons in this hot gas. Think of it like walking through a gentle, steady rain. If you stand still, the raindrops hit your head and shoulders evenly. But if you begin to walk forward into the rain, you encounter more drops on your front than on your back. Your motion through the rain changes your experience of it. In a similar way, a galaxy cluster moving through the sea of cosmic background radiation will leave a subtle imprint. The photons that scatter off the hot gas inside the cluster get a tiny energy boost if the cluster is moving toward the source of the light, or a tiny decrease if it is moving away. This minuscule shift, this fingerprint of motion, manifests as an almost imperceptible change in the temperature of the microwave background in that specific direction. We are not talking about a dramatic hot spot or cold spot. The shift is incredibly faint, a fluctuation of just a few millionths of a degree. Detecting it for a single cluster is a monumental challenge. But by combining the data from hundreds, even thousands, of massive clusters across the sky, a statistical signal can emerge from the noise. It is a testament to human ingenuity, using the faint echo of creation itself as a static backdrop against which to measure the silent drift of the universe's largest structures. This technique does not rely on the light emitted by the galaxies themselves, which can be tricky to interpret over such vast distances. Instead, it uses the universe's own backlight, a uniform canvas painted over 13 billion years ago. Any consistent pattern in the distortions on that canvas, any coordinated tilt in the temperature shifts across billions of light years, points to a coordinated motion. That is the haunting signal of dark flow. It is like trying to measure the speed of a distant ship by only the way it distorts the setting sun behind it. The method is indirect, incredibly subtle, and pushes our technology to its absolute limit. Yet, it is our best window into motions on a scale that defies imagination, a detective's tool for uncovering secrets written in the light of the dawn of time. The most natural explanation is often the right one, but here, nature seems to be defying our expectations. When confronted with a mystery like dark flow, the first instinct of any scientist is to check the obvious culprits, to rule out the usual suspects before declaring a revolution. Could this vast river of galaxies simply be pulled by a known, nearby source of immense gravity? Our own galactic neighborhood is not static. We, along with thousands of other galaxies, are being drawn toward a mysterious gravitational focal point known as the Great Attractor, a region of space obscured by the dust of our own Milky Way. It is a colossal concentration of mass, and its pull is real, but its influence is local, a powerful current in our cosmic bay. Dark flow is something else entirely. It is an ocean-wide tide, a motion that persists for billions of light years, far beyond the reach of any single supercluster, no matter how massive. The Great Attractor is a mountain pulling streams down its slopes. Dark flow is every river on a continent flowing toward a distant sea we cannot see. Another prime suspect is dark energy, the mysterious force accelerating the expansion of the universe itself. But dark energy, for all its profound power, acts in a very specific way. It is not a directional force. It does not pull or push matter in one particular direction. Instead, it is a property of space itself, causing it to stretch uniformly in all directions. Imagine blowing up a balloon with tiny dots on its surface. As you inflate it, every dot moves away from every other dot, but no single dot is the destination. Dark energy is the breath inflating the cosmic balloon. It cannot create a coordinated stream of galaxies all moving toward a single point on the balloon's surface. That would require a dent in the rubber, a slope in the fabric, an external hand pressing on one specific area. Dark energy provides the backdrop of expansion, but it cannot explain the directional tug of war. So we are left with a process of elimination that leads to a staggering conclusion. The source of dark flow is not anything within our 93 billion light-year wide observable universe. It is not a hidden supercluster. It is not a misunderstanding of dark energy. The gravitational pull must be coming from something beyond the cosmic horizon, from a region of space-time whose light has not had time to reach us in the entire history of the universe. This is not just a new object in the distance. It is the suggestion of an entirely unseen landscape, a structure of such unimaginable scale and mass that its gravity bends the path of thousands of galaxy clusters like a distant, invisible mountain range bending rivers across a continent. We are not just mapping the universe we see, we are feeling the shadow of something vaster, a presence written only in the silent, collective drift of everything we know. If the source lies beyond the cosmic horizon, then what exactly could be pulling on us? This question propels us into the most speculative and breathtaking territory of all. The leading hypothesis suggests that dark flow is not a pull from a distant part of our universe, but a gravitational whisper from a completely separate reality. We may be feeling the influence of another universe entirely. This idea emerges from a leading theory of cosmic origins known as eternal inflation. In this view, our Big Bang was not a unique, singular event. Instead, it was the formation of one bubble in a frothing, endless sea of expanding space-time. Think of a pot of water coming to a boil. Our entire observable universe is just one bubble rising to the surface in an infinite, bubbling cauldron. Other bubbles are constantly forming, each with its own laws of physics, its own version of reality, completely disconnected from our own. Normally, these bubble universes are sealed off from one another, their boundaries expanding at speeds faster than light, ensuring they never touch or communicate. But gravity, according to Einstein's theory, is different. It is not a force that travels through space, but a curvature of space-time itself. Some theoretical physicists propose that the immense mass energy contained in a neighboring bubble universe could, in principle, create a dent in the very fabric that separates us. Our universe, our bubble, might be resting on a gentle slope created by the presence of a colossal neighbor. That slope would manifest as a persistent, directional tug on everything inside our bubble, a cosmic tilt guiding the flow of galaxy clusters. In this scenario, dark flow becomes something far more profound than an anomaly. It transforms into a potential keyhole, a tiny crack in the wall of our reality through which we might glimpse the architecture of a multiverse. We cannot see this other universe, its light can never reach us, but its gravity, warping the space we inhabit, might leave a fingerprint in the coordinated drift of our largest structures. It is the ultimate example of cosmic detective work, where the crime scene is all of creation and the clue is a subtle, universal lean. While this idea is exhilarating, it is crucial to temper awe with scientific rigor. This multiverse hypothesis is, by its very nature, currently untestable with our technology. We cannot build a telescope to peer into another bubble universe. The signal is too faint, the explanations too many. For many scientists, it remains a fascinating thought experiment, a narrative that fits the data but exists in a realm beyond empirical proof. Yet its power lies in its ability to reframe the question. Dark flow challenges us to ask not just what is in our universe, but what might lie beyond its very walls. It turns a mystery of motion into a profound philosophical inquiry about our place in a potentially infinite cosmic landscape. This is the quiet philosophical tremor at the heart of the dark flow mystery. Our most cherished assumption about the cosmos is one of profound humility and equality, known as the cosmological principle. It states that, on a large enough scale, the universe looks essentially the same in every direction and from every location. There is no center, no edge, no special place. From a galaxy in the farthest void to our own humble planet, every observer sees a statistically similar cosmos unfolding around them. This principle is not just a nice idea, it is the bedrock upon which all of modern cosmology is built. It allowed Einstein to formulate his equations of general relativity for the whole universe. It is the reason we can look at the cosmic microwave background, that fossilized light from the infant cosmos, and confidently say it tells us about the conditions of the entire universe, not just our local neighborhood. It is a declaration that our viewpoint is not privileged. We are not at the center of anything, but dark flow, if it is real and primordial, whispers a different story. It suggests that on the largest scales we can measure, the universe is not isotropic. It has a handedness, a tilt, a subtle but consistent directionality woven into its fabric from the very beginning. Imagine you are in a vast, seemingly featureless desert. As far as you can see in every direction, the dunes roll on identically, confirming your belief that you are in a uniform, centerless expanse. Then you notice something. Every single grain of sand, when examined closely, has a microscopic ridge or scratch that aligns not randomly, but consistently toward one point on the horizon. The desert looks the same, but its most fundamental components tell a tale of a universal orientation. That is the challenge dark flow presents. It does not mean we are at the center of a cosmic pull, any more than a leaf in a river is the source of the current. But it does mean the river itself has a defined flow, a direction imprinted upon it. This would force a profound shift, not just in our equations, but in our cosmic self-image. We would have to accept that our universe, for all its vastness, might have a structure with an orientation, like a grain of wood with a definite grain. We are not in a featureless bubble, but within something that has a shape, a lean, a history that points somewhere. This redefines our place from being in a uniform ocean to being within a current that has a source and a destination beyond our sight. It transforms the cosmos from a purely random, isotropic expansion into an entity with a narrative direction, a story with a hidden compass point guiding its grandest motions. The multiverse is a breathtaking possibility, but science always searches for the simplest explanation first. Before we cross the threshold into other realities, cosmologists have meticulously explored a middle ground, a realm of exotic physics that stays within the walls of our own universe but stretches our understanding of its infancy. These are not mundane alternatives but profound revisions to the story of cosmic dawn. One compelling idea involves the universe's magnetic personality. We know magnetic fields exist within galaxies and galaxy clusters, but could the newborn cosmos have been threaded with primordial magnetic fields of unimaginable strength? These would not be the tangled fields we see today, but vast, coherent structures woven into the fabric of space-time itself during its first moments. If such fields existed on a cosmic scale, they could have imparted a directional push or pull on the ionized matter of the early universe, setting vast swaths of plasma flowing in a coordinated stream. That initial momentum, locked in during the first fractions of a second, could have persisted for billions of years, imprinting itself as the dark flow we potentially observe today. It would be a fossil of a more violent, magnetically charged birth. Another hypothesis delves deeper into the dark sector. We know dark matter and dark energy dominate the universe's composition, but we understand almost nothing about their fundamental nature. Could they have undergone a dramatic phase transition in the universe's first instant, similar to water freezing into ice? Such a cosmic shift could have sent powerful ripples through the fabric of reality, creating long-range correlations and alignments that seeded a preferred direction for structure formation. In this view, dark flow is not a pull from outside, but an echo from inside, a memory of when the dark components of reality themselves changed state, leaving a permanent directional bias in their wake. Perhaps the most radical idea that still keeps us in our own cosmos is the concept of a pre-existing anisotropy. Our standard model assumes the Big Bang erupted from a perfectly smooth, symmetric state. But what if it didn't? What if the singularity, or whatever preceded it, possessed a fundamental wrinkle, a slight directional preference that was baked into the universe from its very first moment? This initial asymmetry, this cosmic grain, would have never smoothed out. Instead, it would have guided the expansion and the formation of large-scale structure from the very beginning, like a subtle texture in marble that dictates how the sculptor's tools will move. The dark flow would then be the visible manifestation of this primal directionality, a shadow of the universe's original, non-uniform condition. These explanations are no less extraordinary than the multiverse, but they operate within a familiar, if vastly expanded, cosmic framework. They ask us to rewrite the first chapter of our universe's biography, not to invent entirely new volumes in a multiverse library. They represent the rigorous, step-by-step work of cosmology, testing every conceivable door within our own house before concluding that the draft must be coming from a window to another world entirely. The controversy can only be settled by a new generation of eyes on the sky. We stand at the threshold of a revolution in cosmic cartography, where future missions are being designed not just to see the universe, but to measure its subtle motions with a clarity we have never before possessed. The key to unlocking the dark flow mystery lies in vast statistical power, in mapping the positions and movements of not thousands, but billions of galaxies across an immense volume of space. This is the domain of the great surveys, projects like the Legacy Survey of Space and Time, which will be conducted by the Vera C. Rubin Observatory in Chile, and the European Space Agency's Euclid Space Telescope, are about to transform our view. Imagine trying to understand the flow of a continent's rivers by studying a single stream. You might see a local current, but you would miss the grand pattern of the watershed. These new instruments are designed to map the entire watershed of the cosmos. The Rubin Observatory, with its enormous mirror and giant digital camera, will scan the entire southern sky repeatedly over a decade, creating a dynamic, living map of the universe. It will detect and track billions of galaxies, measuring their shapes, distances, and most importantly, their minute shifts in position over time. Euclid, operating from a vantage point in deep space, will complement this by peering far back into cosmic history, charting the three-dimensional distribution of galaxies and the invisible web of dark matter that connects them. Together, they will provide a dataset of such staggering size and precision that the signal of any large-scale bulk flow, if it exists, will either emerge from the noise with undeniable force or fade away as a statistical phantom. This is not merely taking a better picture, it is switching from a still photograph to a high-definition movie of the universe's evolution. By tracing the collective drift of galaxies across billions of light-years, these surveys will measure the cosmic current itself. They will tell us if the flow is a real, persistent feature of the cosmos, or if it was a mirage caused by the limitations of our earlier, coarser maps. We are building the instruments that will finally weigh the evidence, moving the debate from theoretical possibility to empirical fact. The answer is written in the silent drift of countless islands of stars, and we are just now learning how to read their collective language. Theorists cannot build a universe in a lab, but they can create one inside a machine. To test the staggering possibilities of dark flow, they construct entire cosmic histories within the world's most powerful supercomputers. These are not simple animations, but staggeringly complex digital laboratories where the laws of physics are coded into equations and set in motion. Starting from a fraction of a second after the Big Bang, with conditions of unimaginable density and heat, these simulations calculate the gravitational dance of trillions of particles of dark matter and ordinary matter across billions of virtual years. They are our proving grounds for the impossible. Scientists can run two parallel versions of reality, In the first, they create a standard universe that obeys all the established rules, a perfectly isotropic cosmos expanding from a smooth, symmetric beginning. In the second, they introduce a single, deliberate flaw, a seed of anisotropy, a gentle cosmic tilt baked into the initial conditions, or even the hypothetical gravitational tug from a massive, unseen structure lying beyond the virtual horizon. Then they let the clocks run. The question is profound and simple. Does the simulated universe with that initial flaw begin to develop a large-scale, coherent flow of its virtual galaxy clusters? Does a river of digital matter begin to stream in a preferred direction, mirroring the tantalizing signal we see in our real sky? If the simulation consistently produces a dark flow-like signal when the initial conditions are skewed, it becomes a powerful clue. It suggests that our observed anomaly could indeed be a fossil, a relic of a fundamental asymmetry present at the birth of everything. Conversely, if even these deliberately tilted simulations fail to produce a coherent flow on the observed scale, it hints that the explanation must be even more exotic, or that the signal itself might be an artifact. These digital universes offer something pure experimentation cannot, a way to rewind the cosmic tape and play it forward 1,000,000 times with different starting parameters. They allow us to ask, what would the universe look like if it were born with a whisper of directionality? The answer, written in the collective motion of billions of simulated galaxies, helps separate a possible feature of reality from a mere statistical ghost in the machine. The most profound mysteries resonate far beyond the pages of a scientific journal. Dark flow does something remarkable. It transforms abstract equations into a story about our place in the cosmos. This is not just a debate over data points. It is a conversation about the very nature of reality and our desire to understand it. At its heart, this mystery speaks to a fundamental human longing, the need to look at the starry sky and ask what lies beyond the edge of the map. For centuries, that edge was the horizon, then the solar system, then the galaxy. Today, the edge is the cosmic horizon itself, the absolute limit of everything we can ever see. And dark flow suggests something is moving just beyond that final frontier. That idea is electrifying. It turns the universe from a static, if grand, backdrop into a dynamic entity with hidden connections and unseen landscapes. It makes the cosmos feel alive with possibility, a puzzle where the next piece might redefine the whole picture. This is why the story has captivated not just cosmologists, but writers, filmmakers, and curious minds everywhere. It appears in documentaries that try to visualize the invisible pull, in articles that ponder the implications of a multiverse, and in endless online discussions where people grapple with the scale of it all. Dark flow bridges the immense gap between the esoteric mathematics of general relativity and a simple, powerful question a child might ask while gazing upward. Are we alone in this universe, or is our universe itself not alone? This public fascination is a vital part of the scientific process. It reminds researchers that their work touches on the deepest questions we can ask. The intense scrutiny, the debates, the public wonder, all of it creates a cultural momentum that supports the pursuit of answers, even when those answers might take decades or new technologies to uncover. It shows that cosmology is not a dusty, completed textbook sitting on a shelf. It is a living, breathing narrative, a story still being written in the silent drift of galaxies and the quiet hum of background radiation. Each anomaly like dark flow is a new, puzzling paragraph, authored not by us but by the universe itself. We are simply learning how to read it. Dark flow pulls us toward a question far older than telescopes or equations. It asks not just how the universe works, but what it fundamentally is. If this motion is a real signal from beyond our horizon, it confronts us with two deeply different visions of reality, each with its own philosophical weight. The first is a cosmos of chance, an infinite and chaotic multiverse. In this view, our universe is not special. It is one bubble among countless others in a frothing sea of creation, each with its own random set of physical laws. Some bubbles might collapse instantly, others might be utterly barren. We simply happen to live in one where the conditions allowed for galaxies, stars, and life to form. Dark flow in this scenario is just a lucky accident, a gravitational nudge from a neighboring bubble whose own laws are completely alien to ours. There is no design, only infinite variation and blind luck. Our existence is a statistical fluke in an endless cosmic lottery. The second vision is one of a cosmos with inherent structure and perhaps even directionality. The persistent, coherent flow of matter across billions of light years could be read as a fingerprint of something more than random chaos. It suggests our universe, even in its vastness, has a grain, a shape, a narrative arc imprinted from its very beginning. This does not imply a designer in any traditional sense, but it does point toward a cosmos governed by principles that produce order and alignment on the grandest possible scales. It hints that the universe is not just expanding, but flowing somewhere, following a deep-seated pattern we are only beginning to detect. Science, of course, cannot adjudicate between these worldviews. Its tools measure data, not meaning, but a discovery like dark flow does something crucial. It radically expands the context of the conversation. For centuries, our philosophical debates about chance versus necessity, randomness versus design, were confined to the single universe we could observe. Now, the data itself opens a door to a far larger stage. It pushes the boundary of the question outward, from are we alone in the universe to is our universe alone in the multiverse? This shifts the ground beneath our feet. Instead of asking why our one universe seems so finely tuned for life, we might ask if an infinite ensemble of universes makes our particular fine-tuning inevitable. Or conversely, the very presence of a directional signal like dark flow might suggest that our universe's initial conditions were not random at all, but part of a deeper, coherent structure. These are not questions for physics alone, but for a dialogue between physics and philosophy, between what we can measure and what we can wonder. The true gift of a mystery like this is that it refuses to let us be complacent. It ensures that our map of reality always has an edge, and just beyond that edge, there is always another question waiting. This gravitational whisper from the edge of the map sends ripples into the very heart of theoretical physics. Dark flow is not a puzzle for cosmologists alone. It is a challenge that resonates across disciplines, forcing us to examine the foundational rules we believe govern reality. The greatest unsolved problem in modern physics is the chasm between the two pillars of our understanding: the cosmic scale of Einstein's general relativity and the quantum weirdness of the subatomic world. These two theories work flawlessly in their own domains, but they are written in different languages and refuse to be merged into a single, unified description of gravity. This sought-after theory of quantum gravity, whether it takes the form of string theory's vibrating filaments or loop quantum gravity's woven fabric of space, must ultimately describe the entire universe, from the first instant of the Big Bang to the large-scale structure we see today. And that means any viable theory must have room for, or better yet, an explanation for the anomalies we actually observe. A coherent bulk flow of matter on a scale of billions of light years is exactly the kind of macroscopic fingerprint that could help sift through the myriad of abstract mathematical possibilities. It acts as a cosmic constraint. If a proposed theory of quantum gravity cannot naturally produce or at least accommodate such a profound directional preference in the universe's structure, it may be a beautiful piece of mathematics, but it might not be a true description of our physical reality. This enigma becomes a test, a tangible piece of data from the farthest reaches of space that can guide our search for the deepest laws of physics. the pressure extends to another great cosmic shadow, dark matter. We know this invisible substance forms the gravitational skeleton of the universe, the framework upon which galaxies and clusters are built. Its distribution dictates how ordinary matter flows and clumps together. The mysterious motion of dark flow could be a direct consequence of how dark matter itself is arranged on scales we have not yet mapped. Perhaps the flow is not a pull from outside, but a current within an ocean of dark matter that has its own large-scale currents and tides. Imagine dropping ink into a gently flowing river. The ink's movement would reveal the water's hidden current. In this analogy, the galaxy clusters are the ink, and the dark matter is the river. Their coordinated drift might be tracing out the subtle, continent-wide flow of the dark matter sea itself, a sea whose full geometry and dynamics we are only beginning to perceive. Alternatively, the properties of dark matter particles themselves might hold a clue. Some theoretical models suggest certain types of dark matter could interact with itself or with other forces in ways that create long-range correlations and alignments. Solving the riddle of the flow may require us to first solve the riddle of the dark, to understand not just where the invisible mass is, but how it behaves and moves on the grandest stage of all. This is the beautiful, daunting nature of cosmic discovery. We rarely get to solve one mystery in isolation. The universe presents us with an interconnected web of puzzles, where tugging on one thread, like the strange motion of galaxy clusters, inevitably tightens the knots in others. Dark flow, dark matter, dark energy, and the quest for quantum gravity are not separate lines of inquiry. They are different facets of the same profound ignorance, different expressions of a reality we do not yet fully comprehend. A breakthrough in understanding the distribution and nature of dark matter could suddenly make sense of the observed flow. Conversely, a precise mapping of the flow's direction and strength could tell us something revolutionary about the gravitational landscape shaped by dark matter. And any theory that hopes to unite quantum mechanics with gravity must ultimately account for the collective behavior of all these components. We are not working on a single equation. We are assembling a grand, coherent narrative of existence, where every anomalous observation is a clue to a larger truth. The silent drift of galaxies across the void is more than just a curiosity. It is a probe into the deepest architecture of the cosmos, a single question that, when answered, may unlock several doors at once. The search for truth is often a story of 2 steps forward, 1 step back, and a long, hard look at the map. For every breathtaking hypothesis about dark flow, there exists an equally vital chorus of critical voices, scientists whose skepticism is not a dismissal but a demand for greater clarity. This rigorous debate is the engine of discovery, a process that ensures we are not simply chasing phantoms in the data. At the heart of this scrutiny lies a formidable challenge, extracting a whisper-thin signal from a roaring cosmic background. The kinematic Sunyaev-Zel'dovich effect, our cosmic speedometer, is an incredibly subtle measurement. The temperature shift it seeks is minuscule, a fluctuation of mere millionths of a degree against the already varied tapestry of the cosmic microwave background. Critics rightly ask, could something else be mimicking this signal? One major point of contention is our own galactic neighborhood. Our Milky Way is not a silent, dark window to the beyond. It is filled with swirling clouds of dust and gas that emit their own microwave radiation, a foreground fog that must be perfectly subtracted from the satellite data to see the pristine cosmic background behind it. If this subtraction is even slightly imperfect, if our model of this local fog is wrong, it could create artificial patterns that look like a large-scale flow. It is like trying to listen for a distant flute in a symphony hall while a loud air conditioner is running. If you do not perfectly understand the hum of the air conditioner, you might mistake one of its harmonics for a note from the flute. Some researchers argue that the dark flow signal aligns suspiciously well with the plane of our own galaxy, suggesting it may be a remnant of this imperfect foreground cleanup, a ghost in our own machine rather than a whisper from beyond the horizon. Another layer of debate focuses on the galaxy clusters themselves. The method relies on having a clean, unbiased sample of the most massive clusters across the sky. But how do we find these clusters? Selection effects can creep in. Perhaps the way we detect these clusters, often by their hot X-ray emitting gas, inadvertently picks out systems that are already moving in a certain way due to local gravitational pulls. Or maybe the physics within the cluster's incredibly hot plasma is more complex than our models assume, creating a subtle imprint that mimics the kinematic effect. Each of these criticisms is not a roadblock, but a signpost directing the community toward more robust methods. It forces teams to reanalyze their data with ever more sophisticated foreground models, to cross-check their cluster catalogs using different detection techniques, and to run exhaustive statistical tests to rule out chance alignments. This painstaking work is the less glamorous backbone of science, the meticulous polishing of the lens through which we gaze into the abyss. The outcome is still unknown, hanging in a balance of probabilities. Yet this very uncertainty is what makes the pursuit so compelling. We are witnessing the scientific method in its purest form, a collective effort to distinguish a profound signal from an elaborate statistical illusion, all while peering across the largest distances reality allows. The raw data on a screen holds no meaning without the human mind that seeks to interpret it. For Alexander Kashlinsky and his team, the story of dark flow began not with a eureka, a moment, but with a stubborn anomaly that refused to go away. They were mapping the cosmic microwave background, searching for the subtle distortions caused by galaxy clusters, when a pattern began to emerge that contradicted their expectations. This was not a flash of insight, but a slow, meticulous process of elimination, checking every possible source of error, every potential flaw in their instrumentation or their analysis. For years, they worked in a space of quiet uncertainty, knowing their results pointed toward something revolutionary, yet facing the immense professional pressure that comes with challenging a foundational principle of cosmology. The initial reaction from parts of the wider community was one of deep skepticism, as it should be. Extraordinary claims demand extraordinary scrutiny. Their work was picked apart, their methods questioned, alternative explanations proposed. This period was not a conflict of personalities, but the essential, rigorous friction of the scientific process. To persevere required a unique blend of conviction and humility, the confidence to trust one's data while remaining open to the possibility of being wrong. It meant returning to the numbers again and again, subjecting their findings to ever more stringent tests, collaborating with critics to understand their points of view. This human journey underscores a profound truth about how science actually advances. It is not a straight line from hypothesis to triumph. It is a winding path through thickets of doubt, fueled by a persistent curiosity that refuses to accept an easy answer. These researchers were driven by a simple, powerful question: what does the universe actually do, not just what our elegant models say it should do? Their story connects the cosmic scale of billions of light years to the intimate scale of a person at a desk, late at night, double-checking a calculation. It reminds us that every dot on our map of the cosmos was placed there by someone who chose to look, to question, and to endure the long silence before the universe whispered back. This human element, the perseverance in the face of the unknown, is the true engine of discovery, turning faint statistical signals into chapters of our grandest story. The immense scale of dark flow can feel overwhelming, a current moving through a void we can barely comprehend. To grasp its nature, we can look to patterns we already understand here on Earth. Picture the deep ocean. On the surface, waves are driven by the wind, chaotic and changing direction with every storm. but far below, hidden from view, there exist immense, slow-moving rivers within the sea. These are the deep ocean currents, like the great conveyor belt that circles the globe, driven by differences in temperature and salinity. They move with a purpose and a direction all their own, unaffected by the temporary turmoil above. Dark flow is akin to this. The expansion of the universe with galaxies drifting apart is like the surface waves, but beneath that, there seems to be this deeper, more fundamental current, a coordinated drift of cosmic structures on a scale that suggests a different, more persistent kind of pull. Another way to visualize it is to think of an ancient, sprawling forest. From within, the forest seems a place of random growth, trees reaching in every direction. But if you were to step back and see it from above, you might notice something strange. Every single tree across miles and miles exhibits a subtle but consistent lean. They are all tilted slightly toward the east, for example. This would not be an accident of each individual tree's growth. It would be the signature of a persistent, prevailing wind that has blown from the west for centuries, a force whose source lies far beyond the forest's edge, shaping everything within it. Our universe, with its galaxy clusters all streaming in one direction, resembles that forest. The lean is the dark flow, and the wind is the gravitational influence of something we cannot see, a presence from beyond our cosmic horizon that has been shaping the large-scale structure of everything for billions of years. These metaphors do more than simplify. They connect the cosmic to the familiar. They transform an abstract statistical signal into a story about currents and winds, about hidden forces that leave a visible mark on the world. They remind us that the universe, for all its alien grandeur, operates by principles of cause and effect that we can recognize, even if the causes themselves remain, for now, just out of sight. This is a mystery that demands a sharper lens. To hear the universe's faintest whispers, we must build new ears. The next generation of cosmic observatories is already taking shape, designed not just to see the sky, but to listen to its subtlest motions with unprecedented clarity. The debate over dark flow hinges on a signal buried in a sea of noise, and resolving it requires instruments of almost unimaginable sensitivity. Leading this charge is a ground-based project known as Cosmic Microwave Background Stage 4. Imagine upgrading from a single microphone to an entire stadium of listeners, all tuned to the same frequency. CMBS-4 will deploy thousands of ultra-sensitive detectors across sites in Chile and the South Pole, creating a collective ear that can measure the temperature variations in the cosmic microwave background with microscopic precision. Its goal is to map the kinematic Sunyaev-Zel'dovich effect, that ghostly fingerprint of motion, with such statistical power that any large-scale flow will either stand out in stark relief or vanish as a statistical mirage. It will filter out the local foreground noise from our galaxy with a fidelity we have never before achieved, ensuring that what we measure is truly the ancient light from the edge of time, undistorted. Beyond Earth's atmosphere, even more ambitious visions are being drafted. Proposed space missions are being designed with a singular purpose: to directly map the velocities of galaxies across cosmic history. Freed from the blurring and interference of our atmosphere, a dedicated spacecraft could measure the redshift, the stretching of light that indicates motion, for billions of galaxies with exquisite accuracy. This would create a three-dimensional velocity map of the nearby universe, a dynamic chart of how everything is moving right now. Comparing this map of actual motions to the predictions based on the distribution of visible matter and dark matter would reveal any discrepancies with stunning clarity. If a vast, coherent river of galaxies is truly flowing against the expected current, this map would show it as an undeniable blue arrow across the cosmos. The very fact that such monumental projects are being funded and planned speaks volumes. It underscores how seriously the scientific community takes this potential paradigm shift. These are not small, incremental upgrades. They are billion-dollar bets on the possibility that our universe holds a directional secret. Investing in these tools is an act of profound curiosity, a commitment to follow the data wherever it leads, even if that path points toward a reality far stranger than we ever imagined. The machines we build tomorrow will answer the questions we are asking today, and in doing so, they will inevitably reveal new mysteries we cannot yet conceive. The quest to map the cosmos has always been a human endeavor, not merely a professional one. While the satellites and supercomputers searching for dark flow are the domain of major institutions, the curiosity that fuels this search belongs to everyone. Amateur astronomers, with their backyard telescopes and patient nights, play a vital role in this ecosystem of wonder. They are the storytellers and the guides, translating the awe of the cosmos for new generations. By hosting public star parties, capturing stunning images of distant galaxies, and simply sharing their passion, they keep the public conversation about our universe alive and vibrant. This grassroots engagement is the cultural soil from which future scientists grow, and the sustained public interest helps ensure that missions to probe mysteries like dark flow continue to receive support. The mystery does not live only in data sets. It lives in the spark of a child's eye seeing Saturn's rings for the first time, and in the quiet questions that follow. This collective journey extends into the digital realm through citizen science, a powerful movement that allows anyone with an internet connection to contribute to real discovery. Projects like Galaxy Zoo invite people from all walks of life to help classify the shapes of millions of galaxies captured by massive surveys. You are not just looking at pretty pictures, you are training an algorithm or making a direct observation that helps astronomers understand the structure and evolution of the universe. This work, while not directly measuring dark flow, is part of the essential groundwork. By helping to catalog and map the distribution of galaxies, citizen scientists are assisting in building the very charts upon which anomalies like a cosmic flow might be detected. It is a democratization of discovery where a teacher, an artist, or a retiree can log on and for a few minutes help sift the sands of the cosmos for clues. This transforms the search from a distant, abstract pursuit into a shared human adventure. It reinforces a profound idea that the desire to understand where we are and what lies beyond is not confined to laboratories. It is a fundamental part of our story. Engaging with a mystery of this scale is ultimately an act of connection. You do not need a doctorate to feel the weight of the question, to look up at a clear night sky and feel the pull of the unknown. That moment of wonder, that internal whisper asking what is out there, is the same impulse that drives the cosmologist analyzing terabytes of satellite data. Dark flow, in all its elusive complexity, belongs as much to the poet and the philosopher as it does to the physicist. It invites us all to participate in the oldest and grandest conversation there is. By reading an article, watching a documentary, pointing out a constellation to a friend, or simply pausing to look up, you are part of the continuum of curiosity that stretches back to the first humans who gazed at the stars and saw not just points of light, but questions waiting to be asked. This shared adventure reminds us that the universe is not just something we observe, it is something we experience together, a story we are all helping to tell, one observation, one question, one wondering glance at a time. The history of science is written in the margins of error. Our greatest leaps forward often begin not with a grand discovery, but with a tiny, nagging inconsistency, a number that stubbornly refuses to fit the equation. For generations, astronomers tracked the planet Mercury with meticulous care, mapping its elliptical path around the Sun. Newton's law of universal gravitation, a masterpiece of celestial mechanics, predicted its orbit with breathtaking accuracy for every planet except one. Mercury's ellipse itself was slowly rotating, its point of closest approach to the Sun, called the perihelion, was advancing by a tiny, extra fraction of a degree per century that Newton's math could not explain. This was the anomaly, a wobble in the cosmic clockwork. For decades, it was dismissed as perhaps the gravitational pull of an unseen planet, or simply a minor flaw in the observations. But that minuscule discrepancy, that 43 arcseconds per century, became the crack through which a new universe would flood in. It was the precise clue that guided Albert Einstein as he formulated his theory of general relativity. He showed that gravity was not a mysterious force acting across space, but the curvature of space-time itself by mass. When he applied his new equations to Mercury's orbit, the math produced the exact extra precession, no missing planet required. The anomaly was not an error, it was a message, a fingerprint of a deeper, more beautiful reality. Similarly, the baffling constancy of the speed of light, regardless of the observer's motion, was the paradoxical seed from which the entire framework of special relativity grew, reshaping our concepts of time, space, and simultaneity. These were not failures of the old models, but their glorious completion, showing where they broke down and pointing the way to a more fundamental truth. Dark flow stands today as a potential anomaly of similar stature. It is our era's Mercury perihelion, a coherent stream of galaxy clusters moving against the expected expansion is a discrepancy on a galactic scale, a wobble in the universe's largest clock. We can try to explain it away with local effects or data artifacts, just as some once postulated a hidden planet Vulcan to tug on Mercury. But if the signal persists and is verified, it may be the universe's way of telling us our current map, the magnificent standard model of cosmology, is incomplete. It is not wrong, but it is a local map accurate for the territory we have charted, yet silent about the lands that lie over its edge. This historical perspective reframes the entire mystery. The tension around dark flow is not a sign of scientific crisis, but of scientific health. It is the sound of a field listening intently to a faint, persistent signal from the edge of understanding. Such anomalies are the most precious gifts the cosmos can offer, for they do not just ask us to add another piece to the puzzle. They ask us to reconsider the shape of the puzzle itself. They are guideposts written in the language of data, pointing toward the next great theory, the one that will weave together the quantum and the cosmic, the seen and the unseen, into a single, coherent story of everything. The numbers tell a story of persistent tension. When we step back from any single telescope or dataset and synthesize the evidence from the Wilkinson Microwave Anisotropy Probe, the Planck satellite, and the growing catalogs of galaxy clusters, a fascinating statistical portrait emerges. The signal of a large-scale flow does not vanish. Instead, it lingers at a low but consistent level of confidence, typically between 2 and 3 sigma in various independent analyses. In the language of science, this is not a shout of discovery. It is a whisper, a murmur that repeats just often enough to be noticed, yet remains too faint to be declared a definitive fact. Imagine you are in a quiet house at night trying to sleep. You hear a faint, intermittent creak from the floorboards. It might be the old wood settling, the wind against the eaves, or simply the normal sounds of an empty building. But if you hear that same specific creak in the same rhythm night after night, you begin to wonder if there is a pattern, a cause that lies just beyond your immediate perception. That is the current state of the dark flow data. The creak is there. It is not loud enough to be certain of its source, but its stubborn recurrence is what keeps you listening, turning down the other noises in the house to hear it more clearly. This statistical whisper is the heartbeat of the entire investigation. It is why major observatories continue to design missions around it, and why theorists continue to build models to explain it. A signal that was definitively disproven would be a closed chapter, a fascinating false alarm in the history of cosmology. A signal that blazed with 5 sigma certainty would be a revolution, front-page news. But this persistent marginal hint, is perhaps the most scientifically compelling scenario of all. It represents the frontier itself, the precise zone where our instruments and our understanding are being tested to their absolute limits. The universe is not making this easy. It is offering a clue wrapped in noise, a cosmic tug of war between the profound pull of a new idea and the immense gravitational weight of our existing, beautifully successful models. This ambiguity is not a flaw, it is an invitation. It calls for better instruments, sharper statistics, and more creative thinking. It ensures the mystery remains alive, a quiet question mark etched into the fabric of the data, urging us to build a finer ear to hear the universe's deepest secrets. There is a profound comfort in knowing, in having a map that tells us where we are. We have charted the continents of our planet and the contours of our solar system. We have built a magnificent model of cosmic history, a story that seems to explain the universe from its first spark to the grand web of galaxies we see today. Yet, right at the very edge of that map, in the faint statistical whispers of data, we find dark flow. It is a shadow on the chart, a quiet, persistent notation that says our understanding is not complete. In an age where information feels instantaneous and total, this cosmic anomaly is a humbling and necessary gift. It is a reminder that the universe still holds profound secrets, that beyond the borders of our knowledge there are still dragons. This is not a failure of science, it is its highest purpose. To encounter a true mystery is to be given a new question, a fresh direction for our curiosity to flow. The awe we feel when staring into such an abyss is not passive wonder. It is an active, thrilling engagement with the reality that our home is stranger and more vast than we ever conceived. This sense of awe is the engine of discovery. It is what drove the first astronomers to track the wanderers in the sky, and what drives teams today to build billion-dollar telescopes to listen for a whisper in the ancient light. It connects the child gazing up at the Milky Way with the physicist parsing equations, united by the same fundamental question: what lies beyond what we can see? Embracing the unknown is not a surrender to ignorance. It is an honest acknowledgement of our place in a cosmos that is still writing its story. Dark flow, in all its elusive ambiguity, offers us this rare opportunity to stand at the very frontier of understanding and feel the cool, exhilarating draft from a door we have not yet opened. It assures us that the adventure is not over, that the greatest discoveries are still out there, waiting in the dark, silent currents of the deep. The true power of a mystery lies not in the answer, but in the questions it forces us to ask. If we dare to take the signal of dark flow at face value, if this river of galaxies truly flows from a source beyond our cosmic horizon, then we are compelled to imagine what that source could possibly be. Let us speculate responsibly, painting scenarios not as wild fantasy, but as logical extensions of physics that push the boundaries of the conceivable. The first and perhaps simplest idea is one of sheer, staggering scale. What if, just beyond the edge of everything we can see, there exists a structure so immense it makes our entire observable universe seem like a local neighborhood? We call these superclusters and great walls within our own cosmos, but this would be something else entirely. A supercluster, an aggregation of mass on a scale we have no reference for, a gravitational mountain range in the unseen landscape. Its pull would be like a distant, sleeping giant whose gravity gently tugs on the fabric of our own space, setting everything within our view into a slow, coordinated drift toward it. This scenario requires no new physics, only a radical expansion of what we thought possible in terms of cosmic structure. It suggests the universe is far more lumpy and textured on the grandest scales than our current maps can show. Another possibility is even more dynamic, a story of cosmic collision. Our universe in this scenario is not an isolated bubble. It may have brushed against another in the deep past, a fleeting gravitational encounter that sent shockwaves through the fabric of space-time. While the other universe has long since receded beyond any possible contact, the gravitational echo of that encounter persists. It left our cosmos with a kind of momentum, a directional memory imprinted into the very expansion, like a boat still rocking from a wave that passed by eons ago. This would make dark flow a fossil of a dramatic event, a relic of a time when our reality was not alone. Then there is the realm of the truly unforeseen. Perhaps the source is not a concentration of matter at all, but a fundamental asymmetry in the dark energy field itself, a gradient that creates a gentle slope in the vacuum of space. Or it could be a topological defect in the fabric of reality, a cosmic string of unimaginable mass left over from the universe's first instance, whose gravity warps everything around it. Each of these scenarios does more than offer an explanation. It expands our vocabulary of possible realities. They teach us that the universe is not obligated to conform to the limits of our current imagination. The value of this exercise is not in choosing a favorite, but in understanding how a single, faint anomaly can pry open doors to entire new wings of theoretical physics. It reminds us that the map we hold is always provisional, and that just over its edge, the territory may be stranger than any story we have yet dared to tell. The river of galaxies flows on, a silent testament to a universe still writing its own rules. This journey through the mystery of dark flow reveals a cosmos far more dynamic and interconnected than any static map could ever show. From its first controversial whisper in the cosmic microwave background to the staggering possibility of gravitational whispers from beyond our horizon, this anomaly does more than challenge a model. It invites us into a grander narrative. It stands as a powerful reminder that cosmology is not a completed textbook, but a living story, its most exciting chapters likely still unwritten. Every answer we painstakingly assemble from the data inevitably unveils new, deeper questions, each one pulling us further toward the edge of the known. We stand, as all explorers do, on the shoulders of those who came before, using the maps they drew to peer into the dark just beyond the last marked trail. That darkness is not empty, it is alive with possibility, with currents we are only beginning to feel. The flow continues, a gentle, persistent tug on the fabric of everything we see. And so, too, does our quest to understand it. If this exploration of cosmic mysteries has captivated you, consider subscribing for more journeys to the very edge of understanding. We would love to hear your thoughts on dark flow and where you think this river of galaxies might be leading. Share your perspective in the comments below.